Our next presenter is going to be Anita Gale.
All right, so I'm going to try to cover a lot. I started at Rockwell International in Downey in 1974 with my fresh new master's degree in aeronautics and astronautics. Where Downey, California is pretty much right in the middle of the Los Angeles basin. And that's where we did major space shuttle design. NASA people will get you to thinking that they designed the space shuttle and did the analyses. No, it was the contractors at that time, Rockwell International. At first, I was working with all men. Mostly they were Apollo veterans. As I came in sort of early in the program. Most of them were World War II veterans. Many of them were pilots. So casual conversation would include things like, for flying a P-51 Mustang, they preferred to empty the center fuel tank before they emptied the drop tanks. Now, these are just normal things we heard. The buildings we were in Downey were old. Most of them were built in the 1930s. I think some dated from the late 1920s. Mostly they were there for a company called Consolidated Vultee, which during World War II built a trainer aircraft called the Vultee Vibrator. And I've actually seen one of those in the Air Museum in Tucson, Arizona. So they're around, there are a lot of them built. When I arrived in Downey, we still saw the runway markings and the control tower was on the top of building 1. New buildings, quote unquote, new buildings in the 1970s were from Apollo, built in the 1960s. Physically, the buildings in Downey were a wreck. So there was dust on the cubicle, the tops of the cubicle walls, and in the morning we could see where the rats had been because their little footprints were in the dust. There was an area called the aviary because there were birds that were roosting and nesting in the rafters in that area. The roofs leaked in all of the buildings. And we learned when rain was coming where to put the trash cans to try to collect the rain and minimize the damage. And each leak had its own name. So there was a guy named Dick Roble, and when there was a big leak over his desk, that was called Roble Falls. When there were attempts to repair the buildings, the roofs, all it did is it made the leaks move. It didn't really stop the leaks. But despite all of that, we're in these just disasters of buildings. Despite all of that, Downey was a place where magic was happening, and we could feel it. We sensed it. We knew it. We knew that magic was happening there. We were doing things in Downey that nobody had ever done before. So let me give you an idea. The size of an orbiter, this was addressed a little bit in Fred's presentation. So we had a room that dated from Apollo called the Design Engineering Inspection, or DEI room, very large room. And there was most of a space shuttle mock-up there. Now, it was missing the port wing and the top of the tail because they didn't fit, but shuttle orbiter was about the size of a DC-9. The cargo bay diameter was 15 feet. I'm a cargo guy, so that concerned me. The cargo bay diameter was so big that there were payloads that were full diameter that would fit in a space shuttle that we could not fly in a C-5 or a 747. The size was rumored to be set for the payload bay by a classified satellite. I remember talking to some Air Force customers, and they had no idea what it was. So there was something it was designed for, and even we, when we flew classified missions, even we engineers didn't, most of us did not know what was flying. We just did our drawings and did our analyses and worked with the numbers, and that was it. When I arrived in 1974, the outer mold line had already been established. That mock-up in the DEI room was actually a fit check vehicle, or mock-up, and subsequently there were only minor tweaks to the outer mold line of the vehicle, to the basic shape of the vehicle. We already had the designs for the external tank, the solid rocket boosters, the space shuttle main engines, the orbital maneuvering system. So what we were doing between 1974 and when we launched is we were working on the details. Now, and actually the Atlantis exhibit at Kennedy Space Center, I highly recommend that everyone go see that. The Kennedy Space Center Visitor Complex Atlantis exhibit. There's a pre-show movie that summarizes the big design decisions, like what was reusable and what wasn't on the space shuttle system. So by the time I arrived, we were doing the details. So we were doing analysis and test and subsystem design and documentation, lots of documentation. So I remember I was working with Apollo engineers, and during Apollo, the Saturn guys said that you didn't launch the vehicle until the weight of the paper equaled the weight of the vehicle on the pad, and it pretty much was the same for space shuttle, especially in the early days. Bits didn't weigh much, so in the later days it was less so. And we were designing or developing a lot of the processes for operating the vehicles, starting or from 70, the time I was there from 74 until we flew. Now let's think about the 1970s. A big computer was an IBM 360. There was no computer-aided design. There was no computational fluid dynamics. The space shuttle was designed on drafting boards. Now these are big, like pieces of plywood. Maybe they varied in size, maybe 6 feet across and maybe 3 feet, 3.5, 4 feet deep. They were tilted at maybe a 15 or 20 degree angle. They had a drafting machine. So I have a very tiny version of a drafting machine, and you could actually set this. So you could set the angle and how you made parallel lines is you had triangles that you would actually move on the legs of the drafting machine to draw parallel lines. Okay, and this is a tiny drafting machine with full-size triangles. If you wanted to do curved lines, you would plot a few points and use it's hard to see this, and use a French curve. There were lots of varieties of French curves. If you were doing ellipses, you had an ellipse template and you choose the right size for your drawing. The tools we used were, this is a very nice set of drafting tools. Whoopsie, they're falling out, okay? So those are tools that we use. And this is how we designed the space shuttle, with that kind of tools. There were preliminary calculations that were done on slide rules. And I apologize, I know I have 3 slide rules in the house and I couldn't find them when I was looking last night. The big analyses were done with computer programs on those IBM 360s using these, okay? Call them a Hollerith card or an IBM card. It was 1 card per line of code punched into this 80 column card. And if you had a big program, it would be in a box. And I don't remember, the boxes were maybe 500 or 1,000 cards. If you were bringing the box down to the computer room, you had to make sure not to trip on the stairs because it was hard to put them together. And if you wanted to change a program, you would have a few colored cards. You could use a marker, and you could actually see the edge of the colored card in your box of cards. And so now we do analyses with millions of lines of code. Then we were doing them with a few hundred lines of code, which would mean you'd run one analysis to get answers that go into the next analysis, and that's why it took months to do analyses sometimes. Test results were recorded on analog plots, and we literally, to get numbers off of those, we measured the analog plots with a scale like this, just literally measuring by hand. So that's how we were getting numbers for analyses. So this was the most complicated vehicle to ever fly, and we did it with tools that are so crude, most people today don't even remember them or know how to use them, okay? It was amazing what we did. We had great intentions for the Space Shuttle orbiter fleet. When I first arrived, we were planning to fly 50 flights per year when we were fully operational. Of course, we never got to that. We were planning return to the moon, planetary missions, on-orbit assembly, space manufacturing, commercialization. We were talking about all of that in the 1970s and early 1980s. That's another story why that didn't happen. The Atlantis exhibit also summarizes the problems we had. So the initial launch was planned for 1979. Of course, we're celebrating the 39th anniversary. It was 1981 when we first flew, and most of the problems, there are little problems all over, but the big problems were that in test, the space shuttle main engines were blowing up, which is not a good thing, and in test, the thermal protection tiles were not performing. And it was kind of like a race between the two to see which was going to be the long pole in the tent. And miraculously, both of them got solved about the same time. So we were able to fly in 1981. But now we knew during this time, especially from 79 to 81, we knew the whole world was watching what we were doing. And in fact, whenever the space shuttle was in the news, whether it was newspapers or TV or radio, we did have TV and radio then. The adjective that was used to describe space shuttle was problem-plagued. Nobody said space shuttle without saying problem-plagued space shuttle program. And we were living with that, knowing that everyone was watching us. In Downey, we built the, oops, I got a model here. We built the the forward, or the crew compartment, the forward fuselage from this bulkhead at the front of the cargo bay, and we also built the aft thrust structure. The mid-body was built in Wichita. The wings were built on Long Island. The tail, I don't remember where. Orbital maneuvering subsystem, McDonnell Douglas, probably in St. Louis. There were contracts in 48 states. So that's part of why I got congressional approval. The first flight, I'm a cargo guy, so I was concerned or cared about this. The first flight, we had a payload called Development Flight Instrumentation. It was somewhere between 5,000 and 10,000 pounds. And it recorded flight data. There were instruments all over Columbia, the first orbiter to fly. And there was flight data that was recorded. And actually, so the first time we opened the cargo bay doors on the first orbiter, there was little bits of debris were falling out or flying out or coming out just from the manufacturing process. And one of those little bits of debris actually got stuck in a recording head on one of the recorders, so we lost some data. All through the Space Shuttle program, we were making improvements. So you're familiar with this configuration of the stack with the external tank, the colored of unsold dried apricots. Fred showed video from STS-1 where the external tank was painted. And if you see an unpainted tank, then that is either STS-1 or STS-2. And that was actually a process improvement. By not painting the tanks on the subsequent flights, we saved 800 pounds of cargo weight. So Columbia was highly instrumented, and there was a lot of scar weight of wiring that was all over, laced all through Columbia till we quit flying her. Well, she quit flying herself, tragically. Challenger was a little bit less heavy, less instrumentation. And on Discovery, Atlantis, Endeavour, there were the other three orbiters. Each one was a little bit more optimized, a little bit less heavy, but every orbiter had some uniqueness, and especially working with the Space Shuttle cargo bay, we knew this. There were things like on one orbiter, you could use a certain bolt length in a particular bridge for mounting a latch for payload. And on a different orbiter, it was a different bolt length. And if you just did if you had a flight, a cargo complement that went on one mission from one orbiter to another, you had to remember to change those bolt lengths and all those little details that were different on all the vehicles. Once we got flying, as challenging as it was to get going, once we got flying, our customers loved us. It was mentioned in the prior presentation, it was a really smooth ride, probably smoother than what we're flying today with expendables. We had accurate orbital placement. Our first commercial payload was Satellite Business Systems on STS-5. And there was an article, I think it was in Aviation Week at the time, that said because of the accurate placement before their engine burn to get to geosynchronous orbit, they actually saved 1.5 years of station keeping fuel that they didn't have to burn to get in the right spot. And the best mark I consider as an engineer, the best mark I think of a great vehicle, is we were doing things during the program with the Space Shuttle fleet that the original designers never ever expected we would be doing. And that vehicle came through, we could make it do all kinds of amazing things. So that's all I have. I was almost right on time, and I'm happy to accept questions.
Wow, well done. Thank you so much. That
You're
was
welcome.
really enlightening. I liked it a lot. Okay, so questions. Let's see, there was, David Stewart, there was an attempt to build one more shuttle for a private purchase. Do you know why that did not happen?
So I know that we were talking about a blue orbiter, which would have been Air Force. We were talking about repurposing Columbia as a commercial vehicle. It really, I don't remember specifically which one, but it really comes down to cost is pretty much it. And then there are limitations. The range at Kennedy Space Center could only handle so many launches. That's getting fixed now, especially with the Space Force people at Patrick. It's going to be Space Force Base, but Air Force Base are trying to fix that so we can do more launches. But literally, throughout the life of the program, we couldn't have launched 2 space shuttles in 1 week.
Got it. Well,
you had to reconfigure the range for every launch.
Okay. What was the biggest fix done to the Space Shuttle main engines to fix them?
Ooh, That's a good question. I was a cargo bay guy, so I was kind of remote from the SSMEs. I do know a lot of the problems were with the high pressure oxidizer turbo pumps,
Okay.
and they were just I'm not sure what it was. A lot of it was materials problems. You're literally running equipment at the limits of the materials, and it's kind of like a jet engine and turbine blades. We have bigger jet engines now because we have better materials for turbine blades. So a lot of it was just materials limits.
Okay. So then we have another question. Um, this is also from Tapaswini Sharma. What are the most important factors that we must take into consideration? Oh, this is a bit off topic. When we think of a space settlement, can it become a reality anytime soon?
Well, in the space settlement technical community, and that is what we call ourselves, there are some folks who think there will be people living on the, and this is a big National Space Society objective, so it's okay to ask me this. There are some folks who think we might have people living on the moon within 10 years. I'd give it a little bit more time. It's certainly realistic. There are people working right now on establishing mining and manufacturing on the moon to supply commodities. So there are people looking right now at how do we make air from lunar materials? How do we make water from lunar materials? And the idea is that these substances need to be available as commodities. Just like when you buy a house in the US, you call your community and you hook up to the, well, you're probably already hooked to the water line, but you turn on the power and turn on the gas and those kinds of things. So there's an industry waiting to happen. It just is waiting for us to have the capability to get to the moon and start taking advantage of it. And one thing I'd like to say about 50th anniversary of Apollo is humanity is so messed up. I mean, we should have been celebrating these 50th anniversaries on the moon. What's the matter with us? Why are we still stuck on Earth? This is just so stupid. Let's not be stupid like that anymore.
That's right. Let's do the 75th and the 100th on the moon. I applaud
Yeah.
that.
Yeah.
So then we have actually a group question for the ladies. So this is, again, from Tapaswini Sharma. And let's see, where is it? Oh, I've lost it.
Joe, you're doing
Oh,
a great job of running Zoom. Really terrific. Thank you.
I can't find it. I think somebody actually, what happens is people answer the questions and they disappear from my screen. And so let's see if I can find it at the bottom here. The question, and it was answered by Mark Lucas, a guy. No offense, Mark.
No,
It was for the ladies. Do you have any message for the girls who dream to become a scientist?
Well, first of all, the work really gets done by the engineers, not the scientists. That's number one. When I was in college, engineering enrollment of women passed 1%. I got into industry and the percentage of women was like 0.000 unintelligible. So I'm kind of a curmudgeonly, there's those of us who paved the way. So maybe remember me and the fact that there were some trailblazers before me, and I had the privilege of knowing a number of them. And there were some pioneers like me, some sodbusters like me. And girls, you have it much easier than we did. And if you want to ask questions about that, get in touch with me.
Okay, so the girls that live in the present world. So, and I know, I get you that it was tough, okay? I really do. And I can't speak as a guy, but I can at least say that I totally sympathize. So,
I have stories.
so let's see. Karen, what do you have to say?
so I answered a bit in the chat, some quick thoughts, and I also dropped in an email, karen@caltech.edu, if you want to chat with me offline. I grew up in a machine shop, third generation machinist, family business. Grandpa did screw machine parts that put planes up in the air. Dad was voluntold to Vietnam, learned firearms and special munitions, and learned how to take those planes down. That pretty much tells you everything you need to know about generation 1 and 2. So I grew up in this machine shop and a just terrified introvert. I liked machines. I liked engineering and building things and having something in my brain that I could make in real life, it was a lot more predictable than people to me. People were weird and messy and I didn't understand it. And it wasn't because of anything like divine intervention that I can speak to you right now, because my former self from even 20 years ago could not do this today to advocate for people going to space. It is solely thanks to a health physicist in a situation at Caltech when I was in environmental health and safety. I realized all luck was earned, and I had to learn how to self-advocate and be at least an ambivert. And I found Toastmasters, and Toastmasters is a place where it really let me find my voice and help advocate for those who cannot advocate for themselves. So I'm super big into human rights and advocacy. I will say that I give absolute hats off to the women that went before me. I was in elementary school watching the shuttle blow up overhead with my classmates, and my mom's hometown was Krista McAuliffe's hometown. So that was absolutely the reason I never thought about space for several years. And it wasn't until I met another space cadet that at that same age for him, saw a man walk on the moon. And then I realized, bigger picture, we learn from our mistakes. We embrace what we learn, and we also have to have discussions, and meaningful things have to be said in order to bring everybody and lift everybody up. And we can't be defined by our disasters or our mistakes. I will say though, being a female today even, or in 2007 at Caltech, 2009 at Caltech, there's even then, there's a lot that we run into as women that absolutely men don't deal with. When my first question on my job interview was, why do you want a man's job? That was in 2004. Why do you want a man's job? Now, part of that is because the person that was identifying the candidates that was going to be my future boss comes from a culture where Karen, my first name, is a male first name. But he didn't see any other bio or picture, didn't do any homework. And I could have very easily mistook that for something else. And I could have missed one of the best professional relationships I've ever had in my career. So we have to give each other grace and space as far as that goes. I'm really thankful for the question, and I want to let other people also chat. If you guys want to chat offline, please feel free to.
I want to add a little bit to what I said.
Okay.
Some really good advice is when you get into a career, even in college, you're right. You're going to face some different situations from the guys when you're a gal. Just keep your head down, do your job, ignore the crap. Really, that was when I figured out that the guys were going to pull my chain just because I was something different. I just stopped letting them yank my chain, and they bothered someone else.
With me, I had to reject the premise. That was like my thing. In environmental health and safety, I have to get in a big Oompa Loompa suit and consolidate 1H1 55-gallon drums of hazardous materials with PPE and everything. And at the time, I was having my first child, and one of the fellow coworkers who had been there 10 years said, "Oh, well, you might want to dock her pay because she's now half a worker," because I could only consolidate it half the amounts of time. Even though I could consolidate the same amount of time, we had to stretch it out longer because of working in that situation. And yet I was the highest rated environmental health and safety technician. Even though I was the youngest, I was the newest, I just happened to be pregnant. So, I mean, even then, dealing with that, if I just ignored it, I would feel like my silence would make it seem like it was okay, or that I would sign off on it. Needless to say, that person is no longer with the university, but it wasn't for that incident. But he learned really quickly to caution what he said around me.
So I want to move on real quick, but Janet, are you still there? So I'm thinking that maybe she's away from her desk.
Yeah.
Which I don't blame her for. I mean, we've gone on a bit longer. We have one more thing to do. We're not done yet.